All right, let's dive in. Think of this as a kind of mathematical detective story. We've got a suspect, a statement that claims to be true 100% of the time. Our job? To investigate it, follow the clues, and see if we can find that one tiny piece of evidence that makes the whole case fall apart.
So here's our statement, our prime suspect. For all integers m and n, if 2m plus n is odd, then m and n are both odd. Now just take a second and look at that. It kind of sounds plausible, right? It has that sort of mathematical ring to it. But the key words, the ones that should make our detective senses tingle, are for all. Is this statement really true for every single integer you can possibly think of?
So we're not going to treat this like some boring math problem. No, this is a puzzle, and the goal is pretty simple. We need to find a crack in its logic. We're on the hunt for just one single instance where this rule completely breaks down. You know, what's so interesting here is the burden of proof. When a statement says, for all cases, it's making a super bold claim. It's saying there are zero exceptions, not a single one in the entire infinite universe of numbers. Now, to prove it's true, you need a really complex, general proof. But to prove it's false, all you need is one single exception. And that leads us to our main tool for this investigation. We're not going to be building some complicated argument. Nope. We are going on a hunt for the one thing that can shatter this rule, a counterexample.
So, what in the world is a counterexample? Well, it's exactly what it sounds like, an example that runs counter to a general statement. It's that single piece of evidence that lets a detective slam their hand on the table and say, aha, the theory is wrong. In the world of math and logic, it is one of the most powerful ways to take down a claim that's supposed to be universally true.
Okay, this slide lays out our mission plan perfectly. We need to find a pair of integers, an m and an n, that do two very specific things. First, the condition part has to be true. That means when we calculate 2m plus n, we have to get an odd number. And second, the conclusion part must be false. It cannot be true that m and n are both odd.
All right, our mission is clear. Time to start following the clues. And guess what? The biggest clue is hiding in plain sight, right inside the statement itself.
Let's really zoom in on that condition. 2m plus n is odd. Now, the analysis in our source material points us directly at that first piece of the puzzle, the 2m term. This is our big break in the case. So, why is 2m so important? Well, here's the breakthrough. Just think about it for a second. Take any integer, it doesn't matter if it's positive or negative. When you multiply it by 2, what do you get? You always get an even number. 2 times 3 is 6. 2 times 10 is 20. 2 times negative 5 is negative 10. It's a guarantee. 2m is always even. And this leads us to the next logical step, and it's a brilliant one. If we have an even number, which we know 2m is, and we're adding n to it, and the final answer has to be odd, well, the only way that can possibly happen is if n itself is an odd number, right? And even plus an odd is always odd. So to meet our condition, we now know for a fact n has to be odd. Okay, this is the crucial point. We've just proven that n absolutely must be odd. But wait, the original statement claimed that both m and n have to be odd. We know n is locked in, but what about m? Does m really have to be odd? Or could we maybe break the rule by picking an even m? Let's find out.
So, following the lead from our source material, let's just pick some numbers and see what happens. We're going to deliberately choose an even number for m just to see if we can break the claim. Let's try m equals 2. We already know n has to be odd, so let's pick the easiest one there is, n equals 1. Okay, let's check the condition. What's 2 times 2 plus 1? Well, that's 4 plus 1, which is 5.
And there you have it. The number 5 is definitely odd. So the values we picked, m equals 2 and n equals 1, totally satisfy the if part of this statement. The condition is true. We're halfway there.
And now for the final blow. Let's check the conclusion. The statement claimed that m and n must both be odd. But in our test case, n is odd, sure, but m is 2, which is an even number. This flat out contradicts the conclusion. We did it. We found our counterexample. The statement is officially false. Case closed. And that's really the beauty of this whole thing. We didn't need some 100-page proof full of complicated symbols. All it took was one simple, elegant little exception to bring the entire universal claim crashing down. This is the only number you need to remember. 1.
Our single counterexample, m equals 2 and n equals 1, was all we needed to prove that the entire statement, a statement that was supposed to be true for all integers, is completely, definitively false. This is the big takeaway, the fundamental rule of logical smackdowns. If you ever see a rule that says always, or all, or every, your first thought should be to go hunting for that one exception. If you find it, the argument is over. You win.
So, you might be thinking, okay, that's a cool math trick, but what's it got to do with real life? Well, it turns out this way of thinking is an incredibly powerful tool for navigating the world, way beyond any classroom.
So why does this matter? Because we hear these huge, sweeping generalizations every single day. You know, someone says, all birds can fly. A penguin is your counterexample. Someone says, all politicians are dishonest. Find one honest one, and you've broken the generalization. It trains your brain to think critically. Instead of this nodding along, you start looking for that one exception. And honestly, it's just plain efficient. Finding the one thing that breaks the rule is often the fastest way to get to the truth.
So I'll leave you with this to chew on. What's a common belief, or maybe a rule of thumb you've always heard, that might just fall apart with a single counterexample? Give it some thought. You might be surprised what you find. Thanks for joining me on this investigation.